Welcome to the RBFS Fundamentals Training Series. In this short video, we'll explore carrier-grade network address translation. Within RBFS, carrier-grade NAT can be implemented in two ways, either integrated with BNG functionality or as a standalone appliance. We'll walk through both options in this presentation. All configuration examples and demos are based on RBFS version 25.2.1. Before we begin, a quick heads up, this video is free to use for non-commercial purposes and is intended to support self-study with RBFS. Please note that it doesn't cover every possible configuration option, and implementations may evolve in future versions. Here's what we'll cover in this clip. First, we'll explain how carrier-grade NAT works, introducing key terms and the underlying mechanism. Then, we'll walk through the step-by-step configuration process on a system running RBFS. And finally, we'll share some useful commands to help you monitor CGNAT operation. In the following section, we explain how network address translation works and provide an overview of the different types that are available. Network address translation is a mechanism that allows a device to modify the IP address of a transit packet. Optionally, the translation device can also alter the port numbers of an IP packet, a technique known as network address port translation or simply port address translation. The primary use case for network address translation is the aggregation of multiple hosts on a private network behind a single public IP address. This is a common scenario in residential broadband, where a customer is assigned one public IP address but operates multiple devices at home, for example, laptops, tablets, mobile phones, or set-top boxes for IPTV. NAT can also address the problem of overlapping IP address spaces when merging multiple networks. Enterprises often use private RFC 1918 IPv4 address ranges internally, which may no longer be unique when two organizations merge. Another important function of NAT is to mitigate the depletion of public IPv4 address space. IPv4 addresses are 32-bit, allowing for a theoretical maximum of approximately 4.3 billion addresses. However, since some ranges are reserved for special purposes, and others are administratively unusable, the actual number of usable public IPv4 addresses is significantly lower. As a result, NAT helps support the growing number of PCs, smartphones, and IoT devices that require Internet connectivity. Internet service providers use NAT to further aggregate customer IPv4 addresses. While technically similar, the term carrier-grade NAT refers to a highly scalable NAT implementation at the ISP level. In many cases, two layers of NAT are involved, one at the customer premises equipment, translating all customer device IP addresses to a single IPv4 address, and a second layer implementing CGNAT within the ISP's core network. This setup is commonly referred to as NAT 444, as an IPv4 address is translated into another IPv4 address, which is then translated again. NAT can be applied to translate the source IP address, the destination IP address, or both. NAT can be implemented either statically or dynamically. While static NAT maps a private IPv4 address one-to-one to a public IPv4 address which requires the mappings to be manually configured, dynamic NAT assigns private IPv4 addresses to public addresses automatically from a shared pool. While IP address translation is technically possible with IPv6, it is not widely used. One of the main goals of IPv6 was to eliminate the need for address translation. Therefore, RBFS only supports IPv4 address translation. Source address translation is a technique that allows multiple devices on a private network to access external networks using a single or limited set of public IP addresses. It modifies the source IP address of outbound packets so they appear to originate from a public IP address. Usually the private network uses IPv4 addresses defined in RFC 1918 because there are more hosts in the network than public IPv4 addresses allocated to the organization. In most cases, TCP and UDP source ports are translated alongside the IP addresses. This is, strictly speaking, port address translation rather than network address translation. Port translation is necessary because two hosts on the private network may use the same source port and be translated to the same public IP address. Their communications must be kept separate. This technique allows thousands of internal devices to share a single public IP address. In the example on the right-hand side, an IPv4 packet with source address 10.0.0.3 and a TCP source port of 1024 is received on the private or local interface of the CGNAT device. The CGNAT device maintains a translation table that records all active translation rules. In this case, the combination of IP address and TCP port is translated into a source IPv4 address of 192.168.2.100 and TCP source port 4123, and the packet is forwarded upstream to the public interface. If there is another device on the private network using the same TCP source address port, it can be translated to the same public IP address simply using a different public TCP source port, such as 4231. When response traffic arrives on the public interface, the CGNAT device consults the translation table and performs the reverse translation, this time for the destination IP address and TCP port to ensure the traffic is correctly forwarded to the local interface. There are two types of network address translation, static and dynamic. With dynamic NAT, internal IP addresses are mapped dynamically to available public IP addresses from a predefined pool. This is typically a many-to-one mapping. In this scenario, a translation rule is created dynamically when the first packet arrives on the local interface and is removed after a period of inactivity. The advantage of this approach is its ease of configuration and the efficient sharing of public IP resources by internal hosts. However, a key limitation is that connections cannot be initiated from the public network. On the plus side, dynamic NAT can serve as a security feature, as communication can only be initiated from inside the network. If certain devices on the internal network need to be reachable from the public network, static NAT rules can be configured. These are manually created one-to-one mappings that assign a specific internal IP address to a specific public IP address. Destination network address translation is a form of NAT in which the destination IP address, and optionally the destination port, of incoming IP packets is modified as they pass through a NAT device. This allows traffic directed at a public IP address to be transparently redirected to an internal host on a private network. Destination NAT is typically applied on edge devices to enable inbound connections from the public internet to services hosted within a private network that uses RFC 1918 IPv4 address space. Destination NAT is commonly applied in the following scenarios. Port forwarding. Incoming traffic on a specific external port is rerouted to a different internal port or host. Reverse proxying, often used with load balancing or application layer routing to distribute traffic efficiently. Service exposure, allows internal services, such as web, mail, or game servers, to be accessed by external clients, while keeping the internal network structure hidden. To ensure proper return traffic flow, destination NAT is typically paired with source NAT or masquerading. This pairing prevents asymmetric routing, where response packets might bypass the NAT device and get dropped by external clients expecting replies from the public IP. In some cases, destination NAT can also be used to mask public IP addresses within a private network, adding an extra layer of abstraction and control. Let's briefly touch on some limitations of NAT in general. Peer-to-peer applications such as file sharing or online gaming often require devices to establish direct connections with each other. NAT complicates this because internal devices are not directly addressable from the outside. Without explicit configuration, such as port forwarding or NAT traversal techniques, external peers cannot initiate connections to internal hosts. Protocols like SIP, which is used in voice-over IP signaling, often include IP addresses and port numbers not only in the packet headers but also in the payload. Standard NAT devices only translate header fields, which can break these protocols. To handle this, firewalls or routers may implement application layer gateways, which inspect and modify application layer data. However, application layer gateways are often not present in basic NAT implementations and can introduce their own issues. In a traditional IP network, any host should be able to reach any other host directly. NAT breaks the end-to-end connectivity by preventing unsolicited inbound connections, which can hinder innovation and protocol design. This is particularly problematic for decentralized applications and peer-to-peer systems. Many NAT devices maintain stateful mappings with timeouts. If a mapping expires due to inactivity, common in low-traffic scenarios like IoT devices, the connection may drop unexpectedly. This behavior can impact the reliability of systems relying on persistent, low-bandwidth connections. In this section, we'll demonstrate how to configure CGNAT on a device running RBFS, step by step. RBFS supports two types of CGNAT configurations. You can use the CGNAT BNG feature combination, which enables NAT translation for PPPoE and IPE subscribers. Alternatively, you can use the CGNAT appliance, a standalone CGNAT solution. As of version 25.2.1, RBFS supports only source NAT. Note that NAT requires the use of a Qumran 2C or Qumran 2A based hardware switch running a multi-service edge image. NAT is not supported in virtual RBFS images. Before configuring CGNAT, you must first configure the platform profile. The platform profile defines the resource scale available on a hardware platform based on the ASIC in use. Since hardware resources are limited, platform profiles allow allocation of resources based on specific use cases. These profiles are supported only on multi-service edge images. By default, the 4Q platform profile is enabled. This profile supports BNG functionality and allows for 4 queues per subscriber. If you want to use CGNAT in combination with BNG features, you must switch the platform profile to either NAT1Q or NAT4Q, depending on the number of queues required. If you're using the CGNAT appliance functionality, you need to configure the NAT standalone profile. It's important to remember that after modifying the platform profile, the device must be rebooted for the changes to take effect. Now, it's time to put this into practice and configure CGNAT on an RBFS system. Our lab consists of two Q2A based switches running RBFS version 25.2.1. The image is of the multi-service edge type. The two switches, named B1 and B2, are interconnected via a 10G interface. In addition, both switches are connected to a Linux server with an application called BNG Blaster installed. BNG Blaster is an open-source network tester for routing and access protocols, actively maintained and developed by Rtbrick. For more information about BNG Blaster, visit the project documentation on GitHub. We will use BNG Blaster to generate PPPoE client sessions. In this demo, we'll configure the CGNAT BNG on router B1. A standard BNG configuration, including access profiles, is already pre-configured. Let's first check the platform profile with the show platform profile command. As we can see, the 4Q platform profile is active, which is fine for the BNG use case but insufficient for CGNAT. Therefore, we will switch the profile using the set system platform profile NAT_1Q command. Since we don't use class of service in this demonstration, the 1Q profile meets our requirements. After committing the configuration, we need to reboot the system. After rebooting the system, we reconnect to the switch, enter CLI mode, and switch to configuration mode. We can verify that the NAT_1Q profile is now active. We can also see that there are 10 PPPoE sessions active by using the show subscriber command. The show subscriber pool summary command reveals that these subscribers have IP address allocations from the 10.1.100.0/24 network. Configuring NAT in RBFS involves a few key steps. First, we define a NAT pool, which specifies the range of addresses used as public IP addresses. A NAT address pool is created with the set forwarding options address translation pool name command. For simplicity, we will name our pool NAT_pool. The pool is defined by specifying the first and last IPv4 addresses in the range. In this example, we use addresses from the shared address space 100.64.0.0/10, which was allocated by IANA for CGNAT deployments. This address block was assigned to avoid operational issues when using RFC 1918 addresses within a service provider network. If a NAT pool is exhausted, additional pools can be defined and linked together using the next pool option. Next, we define a NAT profile with the command set forwarding options address translation profile name. We'll use NAT_profile as the profile name. The profile must be assigned to an address pool for translation, so we'll link it to NAT_pool, which we just created. We then set the maximum number of translation rules per subscriber to 256. In addition to the pool definition and max rules setting, the profile can be configured as deterministic, meaning that all connections from a subscriber are translated to the same public IP address. We can also set protocol timers for various protocols, including TCP and UDP. For demonstration purposes, we'll set the aging timeout for all protocols to 180 seconds. Next, we need to define the private and public interfaces for our NAT service. It is necessary to enable NAT in the appropriate routing instance using the set instance default address translation true command. Afterward, we define all public interfaces using the set interface name unit number address translation direction public command. In our lab topology, IFP 0/0/3 is the only upstream interface. When configuring NAT in conjunction with BNG functionality, the NAT profile is part of the service definition. Therefore, we create a service profile with the set access service profile name address translation profile command. We will name our service profile service_profile. This profile can include additional service definitions, such as class of service or HTTP redirect services. Finally, we need to assign the service profile to an access interface using the set access interface command. PPPoE subscribers are connected via IFP 0/0/24 and use double-tagged VLANs. After committing the configuration, we must re-establish the PPPoE sessions because the service profile is applied only during session establishment. Modifications will not affect existing connections. The show address translation allocation pool command lists all NAT pools and displays how many resources from each pool are already consumed. The show address translation allocation user command lists the public IP addresses and port ranges allocated to the PPPoE subscribers. In this example, each subscriber is allocated a range of 32 consecutive ports, whether they use them or not. Finally, the show address translation rule command provides a list of all active translations. We can see that BNG Blaster generates some UDP and ICMP traffic, resulting in 2 translation rules for each PPPoE subscriber. Let's take a moment to review the configuration commands we've just demonstrated. To get CGNAT running in RBFS, you must enable network address translation within the routing instance. You also need to define which interface should act as the public or outside interface for the translation. It's possible to configure multiple public interfaces. Next, you need to configure a NAT pool that defines the address range used as the target for translation. The pool is specified by defining the first and last addresses of the range. If multiple NAT pools are required, they can be daisy-chained using the next pool command. After that, you define the NAT profile. The most important component of the NAT profile is the mapping to a NAT pool. Optionally, you can define the maximum number of translation rules per user and configure protocol aging timers. The configuration steps listed on this slide are the same whether you're using CGNAT with BNG or as a standalone CGNAT solution. In the case of CGNAT with BNG, the NAT profile is part of the access service profile, which may include additional services. The access service profile is then attached to one or more access interfaces. This automatically makes the subscriber interface a private or inside interface. In this demo, we'll configure CGNAT in standalone mode. For this purpose we use router B2, which is connected to the BNG B1 via a 10G interface. The device is a Q2A-based switch running RBFS version 25.2.1 with a multi-service image again. The platform profile is initially set to the default 4Q profile. So, we'll change it to NAT_standalone and reboot the system. After the reboot, we reconnect to the switch, enter CLI mode, and switch to configuration mode. We can then verify that the NAT_standalone profile is now active. As mentioned earlier, the initial configuration steps are similar to the CGNAT BNG scenario. We'll go through them quickly. First, we create a NAT pool. In this case, the pool consists of just two IP addresses, 192.168.100.1 and 192.168.100.2. Next, we define a NAT profile and link it to the newly created NAT pool. We set the max rules parameter to 1024, as multiple PPPoE subscribers are already behind a single IP address due to the first NAT stage on B1. We also configure the aging timers. We enable NAT in the appropriate routing instance using the set instance default address translation true command and define all public interfaces. For B2, IFP 0/0/25 is the only upstream interface. So far, the configuration steps are identical to the CGNAT BNG use case. When configuring CGNAT in standalone mode, we need to define the private interfaces using the set interface name unit number address translation direction local command. In our topology, the private interface is IFP 0/0/3, which connects to router B1. We also need to attach the NAT profile to this interface directly, using the set interface IFP 0/0/3 unit 0 address translation profile NAT_profile command. Since this device is not a BNG, committing the configuration will immediately start the translation process. There is no need to reconnect subscribers this time. The commands for monitoring NAT are the same as in our previous example. The show address translation allocation pool command lists all NAT pools and shows how many resources have already been consumed. The show address translation allocation user command treats the private interface as a user, since there are no subscribers. It displays which public IP address and port ranges are allocated to each source IP address. In this example, each source IP address is allocated a range of 32 consecutive ports, regardless of usage. By specifying the user, in this case, the private interface, we can retrieve additional details, such as port usage for various protocols. Finally, the show address translation rule command provides a list of all currently active translation rules. We can see that the BNG Blaster is generating some UDP and ICMP traffic, resulting in a few translation entries. Let's return to the configuration summary slide. We've seen that with CGNAT standalone, the NAT profile is directly associated with the private interface instead of an access service profile. Additionally, the private interface must be configured using the address translation direction local command. So far, we've demonstrated how to configure dynamic NAT, which is the most common scenario. However, in some cases, it is useful to create static NAT rules to ensure that a specific source IP address and source port are always translated to the same address and port combination on the public network. The configuration process for static NAT is the same for both CGNAT BNG and standalone NAT, so in this example, we'll demonstrate it on the standalone device B2. Static NAT is configured by creating a NAT rule using the set forwarding options address translation rule command. We'll name our NAT rule demo_rules. A static NAT rule can include multiple mappings, each defined using an ordinal and an ordinal number. For each ordinal, you need to specify the routing instance to which it applies. You must also define the protocol, for instance UDP, followed by the private or local IP address and the local port. This local address port combination is then translated to the public IP address and port specified in the ordinal. After committing the configuration, you can verify that the static rule has been added by running the show address translation rule command. The output will reflect the static mapping we just created. You can also see that the static NAT rule is not bound to a specific interface, but acts globally. For completeness, this slide includes a quick summary of the steps to configure a static NAT rule. From the attached show command output, you can easily see how the configuration translates into corresponding mappings. To wrap things up, let's quickly go over the CLI commands you can use to monitor CGNAT operation on an RBFS system. There are three main commands. The first two, show address translation allocation pool and show address translation allocation user, give you an overview of how resources are allocated. The third one, show address translation rule, shows all active translation rules currently in effect. I've provided a short sample output for each of these commands for your reference. I hope you enjoyed this short clip on configuring CGNAT in RBFS. If you're interested in using the CGNAT BNG setup, you might want to check out the PPPoE or IPE videos in this series. Thanks for your attention, and see you soon in another video.